Limits at infinity, part 3. The strategy for evaluating limits at infinity of rational functions is to multiply the numerator and denominator by the reciprocal of the term with the highest degree in the denominator, then simplify. Another important tip that we will need is a callback to the fact that if you have the nth root of x times the nth root of a plus b, that'll be the nth root of ax plus bx. Keeping in mind that we have to have this same root here, or else we're going to run into trouble. In this case, we're going to be looking at square roots. We have the limit as x approaches infinity of the square root of the quantity 9x squared plus x, minus 3x. Now, if we try to evaluate this limit as is, we're going to end up with the square root of infinity plus infinity minus infinity. Well, the square root of a number that's getting bigger and bigger and bigger will also get larger, so that'll leave us with infinity minus infinity. Now, we don't really know which infinity is larger. We're not sure if this piece or this piece is getting larger faster than one or the other. So this infinity minus infinity is indeterminate. Now, a common strategy when you end up with an indeterminate form where you have infinity plus or minus infinity is either to factor or to find some way to turn this into a rational expression. So if we look at this, this is equal to the limit as x approaches infinity. And if I just start turning it into a rational expression, that would be 9x squared plus x minus 3x all over 1. And as we've seen as we try to evaluate limits that are indeterminate, if in your numerator you have two terms, you can multiply by the conjugate. So right now we have this guy minus this guy. So the conjugate will just be changing that minus sign to a plus sign. So we'll multiply the numerator and denominator by the square root of 9x squared plus x. Now plus, that's kind of an ugly looking plus sign, but I tried, 3x all over the square root of 9x squared plus x, also plus 3x. So we multiplied by the conjugate here. And it might have been a while, so you might have forgotten, but if we have the quantity a minus b times the quantity a plus b, rather than distributing this all out, this is actually a difference of squares. So this will be equal to a squared minus b squared, which is a lot better than trying to expand this whole expression by distributing our 9x squared to everything and our minus 3x to everything and combining like terms when it's just a mess. So let's use our shortcut. This will be equal to the limit as x approaches infinity of a squared, so the square root of 9x squared plus x squared, which if you square something, like square root of 2 squared is just 2, so we can drop our radical. So that'll be 9x squared plus x minus 3x squared, which will be 9x squared, all over the square root of 9x squared plus x plus 3x. Our 9x's will subtract out. So this is equal to, and I'm going to make that fraction bar a little shorter, is equal to the limit as x approaches infinity of x all over the square root of 9x squared plus x plus 3x. We've done some work, to rearrange this. At least now it's a rational expression of some kind. we have a ratio. If we substitute, or rather, if we try to evaluate this limit now, we're still going to end up with an indeterminate form. But we have a strategy for this indeterminate form. We can divide by the highest degree in the denominator. So if we look at this 9x squared, we have the square root of 9x squared. So this is the square root of x squared is kind of what we'd be looking at there, which is equal to x. So we actually have two terms with kind of the same power in that denominator there. So we need to multiply by the reciprocal of this. Whenever I have a function that has a square root involved in it, I'm going to multiply by the reciprocal of the version that has the square root. So this will be equal to the limit as x approaches infinity of x over the square root of 9x squared plus x plus 3x, and I'll multiply by 1 over the square root of x squared over 1 over the square root of x squared. And this will be equal to the limit as x approaches infinity of, well, x over 1 over the square root of x squared, which I'm running out of room, so I'm going to write it with my little diagonal fractions, if I can. And then we have the same radical here, so we can distribute our x squared inside of the radical. So we have the square root of 9x squared over x squared plus x over x squared. But then for this 3x, that's not under the radical, so I can't use that property. I'm just stuck with the 3x over a square root of x squared. So this is equal to the limit as x approaches infinity of, well, remember, the square root of x squared is just x. So we have x over x, which is 1, all over the square root of 9x squared over x squared, which is 9, plus x over x squared, which simplifies to 1 over x, plus 3x over x, which simplifies to 3. And now we can evaluate our limits. The limit as x approaches infinity of 1 is 1. The limit as x approaches infinity of 9 is 9. The limit as x approaches infinity of 1 over x is 0. And the limit as x approaches infinity of 3 is just 3. So I have 1 over the square root of 9 plus 3. So that's 1 over 3 plus 3, which is 1/6. And this is one of the more complicated problems, because not only do you have to turn it into a ratio by, or quotient by multiplying by the conjugate, which is kind of difficult to recognize, you also have to multiply by the highest degree in the denominator, and you have square roots. So that's a lot of different strategies going on in one problem.